All right, so I'm recording now. Let me pull up the screen to start with the Mentimeter. Okay. Can everyone still see my screen?
Yeah.
Yeah, I can see the screen.
All right. So the Mentimeters, everyone join in. Go to the next slide. We already talked about this video. If you haven't watched it already, let's get ready to go to the first questions. I'll wait until I get a couple more people logged in. Now, with me doing this is just a review to get us warmed up. The goal today is to finish through the second half of the slides while also seeing if we can do some problems today and see how we fare out. So let's see how we make out today, and then we'll go for that. But we're definitely going to finish this content at least after today and try and move on. So let's just start by getting warmed up with some vocab questions. The first question we have: what is a scalar?
Scalar?
Yes, a quantity that is fully described by both magnitude and direction.
Telling you, or is it on?
So
I don't see it on mine.
did it switch?
It's supposed to be on this, right?
Mhm.
I am.
Reload it real quick. Just refresh it. What is it? All right, let's go to the next one. Log out one more time and do it again. A quantity that's fully described by both magnitude and direction, or a quantity that's fully described by magnitude alone, is that a vector? Everyone voted, 100%. Good job. Good job. So we have a quantity that's fully described by magnitude and direction. That's what makes a vector. Now, distance. What is distance? Distance is the amount of ground that is covered, or the overall change in position of the object from start to finish.
I can look at hers though. I can just look at it.
The amount of ground that is covered, good. Displacement. The overall change of position from object start to finish, or the amount of ground that's covered. All right, good, 100%. I don't know why this is.
Me either. I can just look at hers.
You have internet on your phone? Just like get off the Wi-Fi and see if it lets you on. Speed is a quantity that describes how fast or slow an object is moving, or is defined as the rate of which an object's position changes. Oh, it's 100% good. So it's just we're talking about how fast or slow an object is moving. More so looking at the scalar, the magnitude. You know? So velocity, is it a quantity that describes how fast or slow an object is moving, or is defined as the rate at which an object's position is changing? Almost 100%. It is defined as the rate at which the object's position changes. So now we're starting to look at the rates, position over time, position over time. So now looking at the acceleration, right? Is it the rate at which an object's velocity changes, or the rate at which an object's speed changes? It's the rate at which an object's velocity changes. Remember, change of velocity over time, that gives us acceleration. So now from what we just talked about, right? Which quantities are scalars? Just join that site and then put that code in. Which quantities are scalars? Displacement, distance, speed, velocity, acceleration. Good, 100% right. Oh, almost. Good job, Don. Distance and speed are our scalar quantities. So scalars go together, vectors go together. So now after that, which quantities are our vectors? Out of all the options, which ones are our vectors? Displacement, velocity, and acceleration. Those are our three vector quantities. They all go together, especially when we start talking about the relationships when it comes to motion and stat graphs. Guys, look at the leaderboard today. No Sakura. Cassie's in here, right? You're here, right? Okay. Carrie, okay, I see you. Top three. All right. The instantaneous speed of an object, going back to the questions, is the speed that an object has at any given instant or the rate at which an object covers distance. The speed that an object has at a given instant. So that'll come up a little bit later when we start looking at, it's like one problem, like where we talks about speed and looking at the instantaneous speed. So we'll see that in a little bit. So that will come in handy. Now the average speed of an object, the rate at which the object covers distance or the rate at which the object changes its position. Remember, scalars go together. Scalars go together, vectors go together. So saying that, right? So we're looking at average speed. We're looking at the rate at which an object covers distance, right? So we're looking at distance, speed, both scalars. So those two go together. Then we have the average velocity of an object. Scalars go together, vectors go together. So we're looking at the rate at which an object covers distance or the rate at which an object changes position. Good. We're looking at the rate at which an object changes its position. So that's the vector quantity. It's changing your position, talks about the rate, like when you're changing your position, we're looking at displacement more in time. Look at start and finish. So displacement, then go into velocity, which would be the vector. So then the average speed of an object is equal to distance over time or displacement over time. Distance over time, good, 100% correct. Yeah, so now, like I said, scalars go together. So we have both of these are talking about speed and velocity is position over time, but which position are we talking about? We're talking about for the scalar quantity right now, distance over time for average speed. So then we talk about average velocity of an object, and that's equal to distance over time or displacement over time. Scalars go together, vectors go together. Good, 100%. So this average velocity is now, we're talking about displacement over time. So we're talking about our start and finish, and then relative of that over time. Last one. The acceleration of an object is equal to velocity over time or the change of velocity over time. So the change of velocity over time, not just velocity, we have to have a change. We're looking at a rate. Remember, acceleration is equal to the change in velocity over time. One of the most important things. All right, let's do one today. I don't know who was Sakura. Anybody here? Congrats. I see Carrie came in second. Congrats. And Cassie in third. Good job. All right. So before I start the slides, let me check see if somebody needs to be let in. All right. All right, so I might flip my camera back on if I'm going to the board and doing something, and I'll keep myself unmuted. But let me know, can you see my screen on the computer? Can you see my screen? All right, okay, cool. All right, before I get started, let's try and be loud, right? I want to pass out. I said I was coming with binders to make sure everybody had equal an opportunity to be able to study. So, you might have your own. Everyone has a binder.
Thank you. This is good.
As we go through this semester, I will be finding out each one.
So I'm sorry, what screen are we looking at?
Should it say my slide? Do you see 1D kinematics?
Look at the presentation on the speaker.
Is it on Menti? Join the what you call it? Google Meet. So yeah, if you're in class and you want to follow along with the slides, just join the Google Meet. I sent it in an announcement. So I got that out the way. Yes, each level I'll be printing out the rest of them. So like each time we have like a new unit, I'll make sure everyone has it so you can go follow along so it's easier when you see what's going on. Then I can refer to when I refer back to like the questions that we see in the slides. Over there. No, right on that, yes. Okay. That's yours. And then it's easy too when you're ready to do your practice problems, you could just solve them right on there, take pictures, upload it. Good. No, you can just if you wanted to. Yeah. Hold on real quick. Let somebody in.
So are we on how to describe a motion?
We should be on. Are you seeing me change the slides?
Okay. No, we'll be past that because we did interpreting graphs last week.
We are on. We just did position time graphs, so now we're starting at describing motion with velocity time graphs, right? Okay.
Motion with velocity time graphs.
Yes. All right. So now for this one, right? This was similar to what we did in the ones last week, right? When we came through and we had six different options, right? And we were able to go through and we were able to say, what do these kind of look like when we want to revolve and make these drawings? Well, we came up with something similar to these over here and these answers over here, right? So when we look at object and it's moving in its position over time, right? Something moving at rest, something remaining at rest would just be a horizontal line because its position is really not, the rate at which position is changing is not changing over time. So we see it just has a constant velocity, right? So it'd be the same each time versus we see this first one. Sorry, let me go back. We have the position and we have a slope graph, which showing that we actually have a little bit of change. So then we keep moving over. We have slope moving fast, moving slow. But then when we start to see acceleration, we see, I think someone said it last time, the rate at which my position is changing. That's when we get that curved line, right? So let's work a little bit more with that so we know how these work and look at it when it comes to velocity and time graph, right? So we have 1, 2, 3, 4, 5, 6 scenarios. Give me 1 second as we're going here. For my folks that are online, I'm gonna put you in breakout rooms, and then for my people that are in person, I'm gonna have y'all work together real quick, and we're gonna just discuss it, and we'll do a little bit of back and forth on the board. Okay. All right. So I have yes,
Supposed to be drawn on these?
yes.
Okay.
So let me see how I have. I have 14, and then I have here. So I think I'm gonna put y'all 3 together. And then how many questions was it? Give me 1 second. Six again. All right, cool. So let me do 6 breakout rooms. Sorry, I'm gonna do 4. So everyone join a breakout room and then just solve the problems that you're on based off of your numbers. Now I know it's some people that are back and forth. So if you're in class, I want you to work with the people in class.
Professor,
Yes.
we didn't get a chance to get a picture of the problems.
Hold on, let me I'm about to share. See if you
Okay.
can you see that?
Yeah. Okay. Okay.
You got
I
it?
got the picture. Yeah.
Okay.
So it's gonna tell us which one to do, right?
Yeah, so you're in breakout 4, just do problem of 4. So this one, can you see my mouse? This one right here.
Uh-huh.
Yeah, do this one right here.
Wait, I don't see it.
You see that what is
Okay,
the
yeah.
Yeah, do that one.
Okay. Mm-hmm.
All right, give me 1 second to pull the problem back up.
Did you say that? Sorry.
I said, give me 1 more second to pull the problem back up.
Okay.
All right, so we're here, right? Now, does anyone from Let's Go, as we have our people in the back, I'll go on mute in a second, who are describing 5 and 6. For my first group number 1, what did we come up with?
I forget what group I was in, I'll be honest.
The first problem. Anyone for the first one? Constant speed in negative direction, constant speed in positive direction. All right, we'll just keep it moving. What about the second one? Moving in positive direction, speeding up, moving negative direction. What group was that? My pair that was in breakout room 2. Did we come up with an answer? Okay, let's try 3. Breakout room 3. Did we come up with anything? That would be this third problem right here. This might have been a tough one to start off with. So let's try group 4. Anybody from 4?
Sure.
Gotta reload.
For line A moving with positive velocity and negative acceleration, it will be from up to downward.
Yeah, you said up to down.
Mm-hmm.
Okay. And then what do you have for
And-
negative or positive and negative?
Are we on number 1?
Positive and positive, it'll be the opposite. So from down to up.
Down to up. Okay. Okay, I see what you're saying. All right. Now, while we have those 4 that we had in virtual, I'm gonna share my screen a little bit to give my groups that, as in I'm gonna turn my camera on, that were in person to explain theirs. So can I get who did 5?
We had negative velocities, both of them, so they're below the time axis because they're negative. A was negative velocity, negative acceleration. So it's a downward sloping line. And the negative velocity, positive acceleration means it's slowing down. So it's upward sloping till it gets to 0 eventually.
Okay. That's what we got for 5. Now can I get my group 6? We got 2 answers. So I'll let them both explain one by one.
You can go first since I do it first.
Okay.
So my thought process was that since it said that that A is going in a positive direction, I drew it straight, but then it said it's slowing down. So I made it a sharp turn downwards to not fully reach 0 yet because it didn't say come to a stop. So I just drew it downwards. And then B, the same thing, started negative and slowed down. So went up towards the 0.
Okay. Our second explanation.
Thank you.
Yeah, so I think I might have this wrong. So for this one, I thought it was going up because it said positive, and then it started slowing down, so I just made it curved a little bit. I don't know why I did that. Now that I'm talking to you, it might not make sense. And then for the negative, I thought it was going down because it's negative, and then it wasn't a continuum, so that's why I kept it curved, because I didn't think it was a continuous line. So that's why it's curved both ways.
Okay.
And then I didn't know if I did it wrong on this. I was like, even if it goes positive and it slows down, would it come down like this? Like, cause it comes to a stop. That's why I got the point, and then I drew it down. So I figured one of these is right.
Let me stop sharing. Now, when it comes to this one, I'm just curious, right? What are you thinking about the position graph, like how it was curved, and if you see like some type of acceleration?
I think so.
I will say that because this one specifically is the velocity time graphs. So like all these scenarios, just to like summarize, we're looking at if there is acceleration, it'd be constant acceleration. So like,
Constant. I didn't see anything that was constant because it was like it's dropping, it's going up
Mhm.
like this, and then it's coming down, but it's not continuous. So that's why I thought a continuous line would be straight. That's why I kept it curved, because I thought a continuous line was straight.
but the reason why I say that is because if we're looking for constant acceleration, then in the velocity time graphs, we're either going to see a horizontal line or a slope line. If you see a curved in velocity time graphs, that means that you have a changing acceleration, which means that you have like a jerk, like another variable after acceleration. When we see that is what I said like earlier in the year, like I think about like second or third class. When you have a variable acceleration, that's like a drone. Like when it's like going up and down, it's like herky jerky. But like we're not looking at any situations like that in this class. So I'm only saying that because if you're seeing a curve, put it more towards that would be in the position time graphs. Because if it's a curve in a position, then it's going to be a slope line and a velocity, and then we'll have a horizontal line in the acceleration. We have constant acceleration.
I think that's the part that's, I don't want to stay on it too long because I know everybody else is probably not stuck on it. But it's just hard for me whenever you say something is not continuous, right? So that means it's no straight lines.
So think about it as the motion itself, like if we plot it, is going to look like if you see on the screen. You see how it's like continuous, right? So the object is still moving, right? But there's no like breaks in it. Like there's not like, oh, it's a gap in like the line. So that would be continuous. So all these lines are still continuous, right?
So velocity is straight line.
Oh, wait, hold on. No, just the motion is continuous. But now when we're looking at this, right? How is the motion being described? How is it moving, right? So like you can still see my screen, right? You can hear me? Can y'all hear me online?
Yeah.
All right, okay. So like for this first one, right? So it's a continuous motion, right? But what we're talking about is a constant speed. So remember, we're looking at velocity, right? So how is my position? Velocity, the definition is right above. How is the rate of change of the object's position changes? The rate of change of how the object's position changes. So how is my position changing over time? If it's a constant speed, that means that constant speed, how far I'm going, like my position over time is the same rate. So I'm going 11 meters per second consistently. So I'm going 11 meters after 1 second, which means after 2 seconds, I went 22 meters. After 3 seconds, I went 33 meters, and that's constant. So each time that rate is going to be 11. So that's why we have that horizontal line. Now, if it's in a positive direction, it's going to be above the axis, as if I'm going forward. But if it's in a negative direction, going backwards, it'd be below the axis. So positive and negative refer to like the direction that we're going, forward or backwards, right? Same thing now if we see the next one, right? If we see positive direction, but we see speeding up. Speeding up means that we have a variable, we have something for our acceleration, right? But that means that acceleration is my change in velocity over time. So that means in our velocity time graph, we're going to see the velocity changing over time. In that second one, what do we see? The velocity is constantly rising. I'm probably confused you by saying the word constantly, but it's rising, right? It's rising at a rate. Let's say at that rate, it's rising at 11, right? Each time versus the first one is going to be a rate of change of 11 each time, right? This one maybe is changing by 11 each time. So the velocity might start off at 0. Then it's 11 meters per second. Then after 2 seconds, it might be 22 meters per second. Instead of it being a constant rate of 11 the entire time, the velocity is changing. And what does that show in acceleration? Constant acceleration. Now, if we go to the third one, it's the same thing. Slowing down, we're seeing that the velocity is changing. It's changing. It's not a horizontal line where it's constant. It's actually changing over time. We see it starts off very high and it's changing and decreasing as time goes on. In the reverse, in the negative direction, we see that it starts off negative and it's changing and going up towards the 0 as time goes on. Fourth one, same thing. Now, instead of it saying slowing down or speeding up, we're just talking about positive acceleration or negative acceleration. So I think someone came off of mute and said with A, right? We're starting up at the top, right? A positive velocity. But then when we have positive, or I might be looking at the wrong way. No, A was positive, negative velocity, negative acceleration. So then we start positive, right? So we have a high acceleration. But imagine that negative acceleration. That's like if you're trying to slow down your car. So like I'm driving, right? And I want to slow down my car, I hit the brakes. So now I hit the brakes, I start to slow down. That's negative acceleration. Why is it negative acceleration? Because the brakes are created for me to, in the acceleration to go opposite way.
That's what it is. Whenever you say negative acceleration, I'm thinking down.
Just think about direction. So like forward will be positive, negative will be backwards. So if I want to stop my car, I need my acceleration to go opposite direction I'm going. Because then like the brakes will stop, literally make the car stop and then like slow down friction. So that's what you want. But now if I want to go driving example, right? That would be B. Say I want to speed up, I want to go past somebody. So I want to hit the gas so where I have positive acceleration to where I go faster. And you see my velocity increasing over time. So instead of me going 60 miles per hour, I hit the gas, now I'm going 70 miles per hour. So I had a slight acceleration. Now for y'all two examples that were on the board, right? So for that first one, pretty much got something similar to that, which is good. So when we say negative velocity, we mean that we have the direction is negative. So the direction is negative. So we're starting off and the direction is negative. And then when we have a negative acceleration, so that first one, A, right? If we're already in the negative direction, we're below the axis, right? And we have negative acceleration. That means our velocity, our acceleration is in the same direction as the motion of our object.
Wait, say that again?
The velocity acceleration is in the same direction of our object. So the velocity and acceleration are going in the same direction. So basically, if I'm already in the negative and I add negative acceleration, I'm going to keep being more negative.
That's how I look at it for B. Like, you get what I'm saying? I mean, I
Yeah.
know it's not supposed to be curved, but maybe in my mind. I look at it.
So, but that's what you see in that first one with 5, right? And so then in the second one, now you see this X where it gets the shape is because you see it counteracting where, okay, I'm starting out negative, right? But then I start adding positive acceleration. So now I want to get closer and closer to the origin, which would be 0. So like I'm going backwards, but then I want to actually go the other way. So now I have to go turn my wheels, go the other way and stop. And then eventually I come to a stop and go the right direction. So that's what we have when we have that scenario. And also too with these pictures, right? It doesn't always have to be, these are just examples of what it could look like. It doesn't always have to be like A. It doesn't have to start exactly at the origin for it to be the answer to that example. Like you could have started it a little bit lower and then just had to go in a bit fine. It just had to be in the general direction. This is just the example that they gave you. So it doesn't always have to be like, okay, if you didn't have your B at the very top, like at the very bottom at that position, doesn't mean that's wrong. It just needs to show like some similar like motion that looks like that. Now, this last one, right? What they're really trying to get you to understand is not so much the shape, right? But more so how you have a change, like a change in motion. So we're moving in a positive direction, right? So we're just moving in a positive direction. First, we're moving fast, then we're moving slow. So now we're moving in a positive direction. And what that means is you can even assume in this one, just because they're saying moving, that they're not telling you like you're speeding up or slowing down. So you're just moving at like a constant rate. So imagine like you're going in a car and you're just coasting. So you're just coasting, you're just driving, right? And moving fast. Now think about it, right? We talked about it in the Mentimeter. What was the quantity that described how fast or slow an object moves?
Acceleration. Yeah, speed.
Speed, because we're just talking about the what?
Is it distance over time?
There we go. M word, the magnitude, right? So when we're talking about speed, we're just looking at the magnitude because it's a scalar. So when you think about this graph right here, right? An object that's moving in a positive direction, is moving fast, will have a higher magnitude than an object that's moving slower. So when we see this graph where it has this little hump, it's really the first part is you having a higher magnitude to identify that you're moving faster in the beginning. Then the second part is you having a lower magnitude, which shows that you're moving slower. But it's still like in the positive, on the positive end of the axis, right? Now when we see the same thing, right? On the negative is just flip, but just on the negative side and the bottom of the axis. But really for that last one, we're not really seeing, we're still seeing constant velocity, but we're really focused on really looking at, oh, the magnitude is higher because it's higher in the one part, that means it's moving faster. The magnitude is lower at the second part, which means it's moving slower. So that's really showing the difference between, the scalar and the velocity. focusing on the magnitude when we just see the one higher than lower. That's why it looks like that. And coming back to your point, we see that straight line, horizontal line, because it still will show us like you only see like a little small little dip right there where you can see some acceleration, but the most part is just constant. But we wouldn't see a curve in this one right here because we're always talking about constant acceleration.
It's basically saying it is constant without using that word. If it's just saying it's moving and it's not giving you like speed, it's just like you said, it's coasting.
Yeah, I would say with this one, the wording for this one is weird. You're not crazy. Like this one is a little weird, but for this one right here, you can assume that it was saying like it would be constant. Yes. That one was a lot to start off with, but it really just kind of brings home the entirety of what we're moving forward to with this section. So let me just go to the next one. All right. So we're going to do it similar like this right here. Everyone take a picture real quick. There's going to be a lot of just talking to each other today, only because the way that you really get this is by talking. So now this one, we have 5 different graphs, right? So what we want to do is now we got the hang of what the graphs look like when we see like different types of motions, right? So like if you see, let me just do a quick quiz. If you see a curved line in the position graph, what does that tell you? There we go, right there. You see acceleration. Say it again. If you see a curved line in a position graph, you know it's some type of acceleration. Now let's see, you see a slope line in a velocity graph. What do you see? Constant. Constant acceleration. Whoever said that. Yes. So if you see a curved line in the velocity graph, a straight line, a slope line, something like this. Like this. In the velocity graph, you know you have constant acceleration. What do you, if you see a slope line in the position graph, you have
Velocity,
constant velocity. And if you have constant velocity, do you have acceleration? No, because acceleration is there we go. So if there's constant velocity, is there change in velocity? No. Yes.
What are some situations like in the world where you would see the curved velocity time?
Drones. Yeah, because like drones, like they go like they're not like in a car you're just driving but you're still level. Drones, because they fly, they're not like just like this. They're actually like, you can see it like when a drone is moving, it's like kind of like jerking like up and down. That literally that last like scale like measure of motion, like if you see like a variable acceleration, because if you have a curved velocity, then you'll have some slope type acceleration. That one underneath it, you can look it up. It's called jerk. Jerk is like underneath. When you have a acceleration that's changing, then you have jerk underneath, and you usually see that with drones. That answer your question?
So that means it's all over the place.
Yeah. So like you've seen a drone move before, right?
So drones are all over the place.
So that's the biggest thing, is like trying to control like how, because that's even like if you were flying, like if you're flying in a plane, like you're gonna be flying, like we feel like, oh, we're just moving, but like the plane relieves like.
Yeah, that's what she was trying to tell me. So that's why I made sense.
Yeah.
But
So-
she said if it's constant, it's like this. If it's continuous, it could be like.
Yes, but that's still continuous. Like that's still continuous. Like now would be like, this is like more of a math thing, right? So all these lines, there's no breaks, right? Something like this. That's like discrete, because you see a break in it. Now this you'll see in like signals. Like in signals, like you'll have some signals that have like discrete where they like that. That gets more into like digital, like EE, computer engineering type stuff. That's like my domain. But in this class, we're not talking about nothing like that. We're all looking at continuous motion. Now, with that being said, I did a quick little quiz just to get you going, because what we want to do is take these 5 graphs, right, and relate them to actual scenarios, right? And so each time we're talking about an object, we want to look and see which graph matches with the object, right? So I'm going to give everyone a verbal description, and you have to pick which graph you think matches with it. One more time. We got 2 groups in person, so I'm gonna do 3 breakout rooms with everyone else. Once again, if you are online, let me make sure that you can see the problem. Oh my gosh, I did not mean to do that. All right, one more time. I definitely just flashed the answer, but if you didn't see it, good. All right. I'm changing the names of the breakout rooms to the question that you're doing, and I'm about to send you. Take a picture of it right now. In 3, 2, 1. All right, go. So I want y'all to do D, and I want y'all to do E. All right, okay, we got everyone back in the main session. So now I want to hear more of your thoughts. So I'll start with our first group, Group A, who had verbal description A. What did you come out with?
I thought it was D. Can you hear me?
Sorry. Go ahead. Yeah.
We thought it was D. That was the only thing that kind of looked right for me.
What answer did he say, D?
Yeah, he said D. Go ahead. Why did you pick D?
It's a velocity graph. The object is moving fast with a constant velocity. The velocity is constant up above, so I kind of just went, oh, it's going fast, you know, and then moves slow with a constant velocity. And what I thought it would be was more like a straight horizontal line, and then a drop in vertical, and then another slow constant. But there wasn't anything like that, so we settled on that. You know, I don't know though. I could be very wrong here.
No. We're gonna get to the explanation a little bit. I like you coming off and explaining what you thought. It's good. My verbal description B.
I think it's B. Because it says it's moving in one direction with a constant rate of acceleration. And then it continues in the opposite direction with the same rate of acceleration. So that would be a straight line going down.
So you said, say your answer one more time. You said
B.
B. Okay. So we got D, then we got B. All right. Okay. All right. Let me get to third group. The object moves with a constant velocity and then slows down. What'd you say?
I said it was E because it says the object maintains a rest position for several seconds, then accelerates. So in the graph, you could see it's straight and then it curves up. And you said once the graph curves up, it's an acceleration. So
Oh, I see what you did. Did you?
yeah, that's
Did
why I
you?
said E.
You said which one did you do?
C.
As in you did graph C.
Yeah.
Oh, okay. I wanted you to do the verbal description, but you're saying
Oh.
graph. Yeah.
Oh.
No, that's cool. That's fine. That's fine. You said
Mhm.
graph C, you correlates with E, right?
Mm-hmm.
All right. So I'm gonna come back when we go to the last group and see if they get the same answer as you. But that was good. All right. All right, now we're going in person, right? So my first group in person. Hold on. Can you give me an explanation for verbal description? Who's coming off mute? Hold on. Give you the spotlight.
Hello. We said it was graph A because it's a velocity time graph that moves in a straight line and then goes diagonally.
Okay. So we got graph A for verbal description D. All right, who's coming off mute? Who's representing? All right.
So for E, we went with graph A because it's a velocity graph and it talks about a rest position for several seconds and then you have a constant acceleration.
So for E, you got A.
Yes.
Okay.
Correct.
So let's go through and let's see what we got. I do like that everyone went ahead and was able to at least articulate an explanation for their thought process. That's the first step in making sure we get this down. And so let's really take it one step at a time to really see what's really going on. You can still see my screen, right? All right, let's go through these answers, right? So for the first one, right, we have the object is moving fast with a constant velocity and then moves slow with a constant. Am I reading that right? Moving fast with constant velocity, moving with a constant velocity. Hold on real quick. No. So, yeah. So what's happening right in the first one, right? So moving fast, remember constant velocity. So constant velocity, how does the line look? Oh, perfect. That's exactly the thing too. So E, right? What's the two axes? Obviously the bottom one is time, but what's on the left? Position, right? So now what position, right? If you see a slope line of position, what does the velocity look like? slope line, not curve. Constant. So it's going to be what type of line? If it's constant,
No change of velocity. Like that's me.
if it's constant, it'd be straight. Is it look like this or does it look like this?
Oh, the first, like, well, not this.
If it's constant, remember, constant lines look like
Straight on.
straight, but which way? Slope or horizontal?
Horizontal.
Horizontal. But why is it horizontal? Think. Constant.
Oh, because it's just going in a straight line almost.
Don't just say it's going in a straight line. If it's constant, what's happening?
It's not changing.
Not
Direction.
not changing, right? So if I'm going 60 miles per hour, I'm continuously going. So after 2 seconds, how fast am I going?
60.
After 5 seconds. So I'll just keep going. So it'd be 60, and then it'd be 60 again, then 60 again, and 60 again. So then that line is going to end up being
So because it's
horizontal.
going fast, it's going up.
Now think about what he's talking about with E, right? I know we were having a debate back and forth, right? So now position, right? My position is changing, but at what rate? Is it changing to where it's variable to where I see a curve? No, it's changing at a rate that's constant. So that rate is going to be the same in my velocity each time. So how much did that change by? 11 meters per second. After 3 seconds, how much did that change? It's 11 meters still per second. So that velocity is going to be the same the entire time, which means it's going to be a horizontal line in the velocity time graph. Now, why are we saying that, right? Because now it's going to be a constant velocity, fast. Yeah, I'm looking at graph E for A. So now that's what I'm saying. When I'm saying position time graph, what would the velocity time graph look like? A horizontal line, which means constant velocity. But it's going to be like how that one we just did. I don't know if you can see this. You see this one? The one before? 6. Remember how we talked about magnitude? And so its magnitude is higher when it's fast, magnitude is lower when it's slow. Same thing here. Now the difference why I'm focused on saying the position time graph and how you have to imagine the velocity time graph is because that first part, right? How does the line look? It's a slope line in the position time graph, but is that one steeper? Like, would it be harder to go up that hill versus the other one? Yeah, so that means that line is more slope. So if you were to actually take the slope of that line, the magnitude would be higher, which means that it's moving faster. Now, if you take the slope of the next line, that means the magnitude would be lower because that line is not as slow, which means it's going slower. So that's why E is that first one. Very confusing, but are you able to follow some parts of what I just said?
Yes, some parts.
Yes. Go ahead.
I'm drawing the velocity time graph for visual aid. Just for-
For that one I just did.
Because it's like talking about a graph is like hard to follow.
I was trying not to. Yes. I'll do it. That's funny. I had to draw it like little line right there because it is going to change. But like this is how it looks. Give me 1
The
second.
bottom one is the bottom.
Yes. For my people online, give me 2 seconds. So I just drew this on the board. Oops. I don't know if we can see with the glare. Can you see this? I'm trying not to move, but can we see this?
Yeah.
Okay. So this is actually what's going on when I'm talking about in problem A, right? So the position graph looks like the first one in red above, right? But to understand how the velocity, we would take the slope to be able to see how it changes, right? So now, and it's a slope line, right? So that actual velocity is going to be constant, which means it's going to be a horizontal line. But because this lines are very steep, it's going to be a higher magnitude, which means it's going to be above this other line. This one is not as steep, so it has a lower magnitude. This is what symbolizes it to be. This is fast and this is slow. So this is what's really happening to velocity, but the position graph that matches what we see in the velocity from the verbal description looks like that, which ends up being graph E. Any questions about that? All right. Now let's go back to how to even, and that's very key to look at when we look at the position time graphs, right? To be making sure that we're looking at really just the axes, like for all which one's going through. Let me just look at another one, right? So C is a position graph, right? So now, with C being a position graph, right? What type of motion do we see in C? It's what type of line? Curve. So now that we see a curved line in position graph, we know that we're going to have what in the velocity graph?
Position. Acceleration.
We have acceleration because we're going to see a what in the velocity graph? A slope line, right? Which means in the acceleration graph, we'll see a line above zero, horizontal. But we know we have acceleration. So now that we know we have acceleration, I'm saying that we know we have acceleration from C, right? I'm going backwards. I'm looking at graph C only because it was position. Which verbal description talks about something accelerating? That is true, yes. So E, right? So that literally that one right there, right? So the object maintains a rest position for several seconds, then accelerates, right? So now that's why that one is E, because rest, what means my position is not changing. So if my position is not changing for a little bit, it will be constant. So now we see a horizontal in the beginning, right? But then all of a sudden, I start to accelerate. So I'm changing my position, but I'm not changing it at a nice, easy rate. I'm changing it really fast. So now you see that kind of sharp, like, ooh, like it just goes whoosh. So that's what we see the acceleration right there with that one. So that's what we can tell from the position graphs. Now the rest of these are all velocity graphs, right? So now these ones should be what we just seen beforehand. So like if I look at B, verbal description B, right? It says it correlates with graph B, right? So the object is moving in one direction with a constant rate of acceleration, slowing down, then it changes direction. Now, from the graph mathematically, right? Remember, when you change direction, you have to come to a full stop. So a full stop means your velocity is what? Zero. So that means that you have to cross the time axis. So which graph represents you crossing the time axis and your velocity being zero? B. So that's what it said. When you know you're changing direction, you have to come to a full stop, which means that I have to cross the axis on that graph. So now let's look at C, right? Moves with a constant velocity, then slows down. Constant velocity, then slows down. Slows down means what? You see what? Some type of change in velocity, decrease, which leads to acceleration. So I need to see a change in my line, right? So that first part, which we see with D, right? It's constant velocity, horizontal. It's not changing. Then all of a sudden, my velocity starts changing. And then how does it change? It's getting more negative because I'm slowing down. So that's where we start to see that change in velocity. Then we go to, I think the last one, what I didn't cover was D. The object moves with constant velocity and then speeds up. So if we just said the first one was constant velocity and we slowed down and we went horizontal, then we went down, right? What does constant and then speeding up look like? Horizontal then, yes, which was which graph? A. So we went horizontal because it was constant. Then we sped up because we have a change of velocity, but this time it's increasing. So now we go up, up. And to be honest with you, it will look more if he was in the position graph. It will look like that won't look like a curve like that. So that would be there. But like that's how do you can see what those are describing it graphically.
There was a position time, we were saying it would be
Yes.
straight and then a curve.
Yes.
Constant.
Exactly. Yes. Yes. Yes.
Wait, say
There you
that
go.
again?
One more time. Say it exactly like that.
If we did a position time graph for verbal description D, then we would have a straight upward slope and then turning into a curve.
Mm-hmm.
You go
Exactly.
constant first and then speeds up.
Mm-hmm. All right. Good. Thought we were done? Nope, not done. Okay. We're really hammering this graph thing because this leads us right into equations, right? It's actually kind of moving. I'm kind of glad that this graph is taking a little bit longer because the graphs are really to explain how we get to just going to just get to equations. But for real, do not focus. Houston, yes, do not get stuck in focus on just the numbers. This is very conceptual. Even though you see a graph with numbers right now, still be very conceptual on how we go about it, right? All right. Let's try this a little differently, right? Let's talk this one through together as a class. And I can go back and forth between online and who's in person, right? So let's just come up with some answers and let's talk it through. So for this first one, right? What we're trying to analyze is this whole situation to see each student. So that's like if all of y'all were looking at this motion, right? And y'all were coming up with your own justifications of what's going on. So each student has their own idea of what they believe is going on. So now because of that, we want to see who's right and who's wrong. So let's read each one and go through, right? So after the first one, right? The student says, after 4 seconds, the rocket is moving in the negative direction. You say yes. Why do you say yes?
Down to the negative. Past that.
After 4 seconds. After 4 seconds.
After a few seconds, it starts to go down.
Okay. And we're looking at a velocity time graph. I seen you shake your head. What'd you say? Okay. You say no because it changes direction after it crosses the 0 at 9 seconds, which would be a stop. Anybody else? I heard somebody else over here.
Still above the time axis, so it's technically still positive.
So you said it's above the time axis, so it's still technically positive, not negative. Okay.
Say yes because it came to a stop.
So we got yes, because it comes to a stop, it goes to go down. We got 2 no's. I got a yes in person. I'm looking at the chat. Anybody say yes, no in the chat or want to come off mute and explain? I got a 3rd no in the chat. Okay. So we got a few yeses and nos. I got 3 no's, so I'm gonna say no for the first one is the winning one. But we'll check at the very end. I'm not saying it's right. I'm just saying more people pick no. So as a class, we'll consensus say no for the first one. Now for the second one, right? The rocket is traveling with a greater speed during the time interval from 0 to 1 than the time interval from 1 to 4. So basically, they're saying from 0 to 1 is a greater speed from 0 to 1 versus from 1 to 4. Yes or no? I got some yeses.
Wait, I want to make sure I got this right. So they're asking. The rocket is traveling. I say no.
I got a yes. Why'd you say no?
I said no.
I heard you too. Okay, so you said the interval from 0 to 1 on this velocity time graph represents acceleration. Okay, and why'd you say no?
Because it's not, it didn't reach the peak. I forgot what's the word. Full speed, because it has to reach like full speed. The peak.
Peak.
It looks like it's still going up.
Compare from 0 to 1 and how about from 1 to 4? Which one you think has a greater speed?
So 1 looks like it because it's close to the 40, but then from 4.
1 to 4. As she's going, chat. What's the chat say?
Don't we have to calculate?
I said a yes. I heard a yes. I do not want you to calculate it. I actually want you to eyeball this. Stay away from the math as much as possible. I see a yes in the chat. Anybody else in the chat or want to come off mute? I got 2 no's. I got a yes online. Do I have another yes? So you got 2 yeses. We got a tie. I need somebody to break the tie.
We still on number 2, right?
All right. So for number 2, we're going with yes. Now we move to 3. The rocket changes its direction after the 4th second. And what did you say for number 1? Okay. So I got a yes. I got a no. Anybody else? For number 3. Chat. I got another one for no for number 3. No is in the lead right now. Yeah. All right, we got another no. All right, so number 3, with consensus, we're saying no. So we got no. Wait, did we say yes for number 1?
I said yes. The rest of the
Wait,
class
who
said yes.
who won? Who won? Was yes for number 1?
It was no one.
No one for number 1?
No one for the first one.
Okay.
Yes one for the second.
So we got no, yes, no. All right, okay, all right. What we got for 4? During the time interval from 4 to 9 seconds, the rocket is moving in the positive direction, up and slowing down.
Yes.
We got some no's. Why'd you say no?
If I say it's 4 to 9 seconds, the rocket is moving in a positive direction. No, because it's going down.
You said no because it's going down
Yeah, towards the axis.
towards the axis, so that's why you're saying no. Okay.
It's going down towards the axis. I said slow down.
Is that why you're saying? And you're saying?
Yeah, it's going towards 0. But it's saying, is it moving in the positive direction?
Yes.
And slowing down?
Yes, because it's still above the time axis, so it's still positive.
I say no, because the line, it's not where it's at. Yeah, it's still on top of the 0. It didn't go past the apex, but it's still going down. It already came to a stop and I was going down.
So you certain on no.
I'm saying,
And you're certain on
she said yes.
Yes.
yes. Anybody else? I got another yes. Anybody in the chat? For the 4th one, are we saying no or yes with justification? I see yes. What's that? Did you say, Cassie, did you say yes? So I got 3 yeses. All right, so we're going yes for the 4th one. So we got no, yes, no, yes. All right, last one. At 9 seconds, the rocket has returned to its initial starting position.
Yes.
You said no. Why you say no? Okay. You said it started at 0, then it went past the starting point as it continued to go down.
I say no.
You say no.
I mean, I say yes,
No.
I say yes. And
Or you say yes.
Yes, because it's staying right there on the apex with the starting block.
Okay. You said it's at the apex with the starting point. You said no. Why? Okay. The displacement changed. Okay. What'd you say? It's back to its original velocity of 0. Okay.
Yes.
Is it not a position graph? It's a velocity graph. Okay. Is that what you were saying too?
Oh, yeah, because it's just reaching 0 velocity, not 0.
Bridge to zero velocity. I'm just so okay. Raise it. Wait. Let me tally it up. Did you say? You said no. No. No.
She said no.
Okay.
I
I'm
said
a
yes, I'm the only one.
chat. I see another no. All right. So no there. So all together we have no,
Yes.
no, yes, no,
Yes.
yes, no.
Yeah.
All right. Who thinks we're right?
Think I'm right for a
All right.
lot of them.
Let's see what the answers are. All right. So we got no, 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 yes, no. So what was that? How many we got right? We got the first one right. No, 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 yes, no. Oh, I'm about to explain all of them. Yeah. Which ones did we get incorrect? Oh, so we only got number 2 wrong. All right, so see, we did 4 to 5. That was all right. That was all right. All right, let's walk through these real quick. So the first one, just because we got that one right, but yes, after 4 seconds, the rocket is moving in a negative direction. So the negative direction actually starts, I think you said it, Carrie, right? At 9.
I don't
But I think
I've talked myself out of it.
so really is that 0, because we're at the velocity time graph, that 0 means 0 velocity, which means when we reach 0 velocity, say if we're above the axis, we're in the positive direction. But then if we hit the 0, that means we're coming to a full stop. So positive direction moving, full stop, then we go in negative direction. That means we changed our direction. So that 0,
I'm confused now.
hold on. That 0 means we're changing our direction. So now we need to find when we hit 0. When we hit 0, what time? 9. After 4 seconds, we still are on the positive, which is in the top half. So we didn't change our direction yet.
Isn't this with the other graphs?
Yes. That's what you're doing. The position graph. So now think about it, when you see velocity, a change in direction of the velocity graph, we cross the axis.
Wait.
That line in the middle, that axis.
Okay, so when you cross 0 on velocity, you change direction.
Correct.
Period. Okay.
Yes.
So at 4 seconds, you're basically starting to decelerate. Has nothing-
Yes.
has nothing to
You're
do with direction.
what? You're what?
Slowing down.
Slowing down. So what?
The only way to change direction is crossing that x-axis on.
So
your
wait,
graph.
say what you just said. Say what you just said. At 4 seconds, you're starting to,
Decelerate.
which means you're,
Slowing down.
which student's answer? Look on the question. Number 4. So number 4, they said during the time interval from 49 seconds, the rocket is moving in the positive direction up and slowing down.
She was saying that I was thinking about the other graph. This
Yes.
was the other graph. Maybe that's what it is.
So that's why you got to look at it and see which graph we're talking about. The very top, it says velocity versus
This is my
time.
So I think I have to
Yes.
train my mind
Mhm.
to look at it different.
Just look at it first and see what it says. It says velocity time. Now I'm looking at velocity. If it says
So the
position,
regular graph, I would have been right?
yes.
Position graph isn't necessary. The directional change is always at 0.
Oh, we don't need it for right now. We can look at the velocity graph and we can figure it out. The velocity graph does tell us a lot of information. It does, because it goes back between, because velocity is right in the middle. So it can tell us about position, and it can tell us about position, and it can tell us about acceleration.
So- At the 4 to 9 second period, it's slowing down, but it's still going up,
Yes,
right?
like it's still in the positive direction.
Like,
Let's say up is positive. Like
yeah, like the rocket.
like it's a rocket, yes. So going up. So it's still going up, but it's slowing down.
That's what you were saying, but it was like my mind was still.
Like when you shoot off.
It looks like it's going up and coming down, but it's not.
I was thinking about that.
That would be a position.
Yes. And then now you got after that, right? So that just did that one, right? So now, oh, I want to come back to 2. Oh wait, so now we can do that, right? So that goes, we know 1 and 4, right? We understand how those were the correct answer, right? So now let's go jump to 3. The rocket changes its direction after the 4th second.
Yeah, because it's.
Oh,
Oh, no, because this is a velocity graph. That's right. It's still in a positive.
exactly. So now you see how it all goes back?
Yeah, so it's easy for me to understand if you explain it.
Yes. So now we got that 4th one, right? So now let's think about it, right? Now I'm jumping all around. Now I'll go to 5, right? At 9 seconds, the rocket has I can't even speak. Returned to its initial starting position. Now, what does that really mean at 9 seconds when we hit 0?
It stops.
Exactly. It stops. But did we return to our initial position?
No,
We don't know that. We just know that at least it stopped.
but okay, so let me get started. For a velocity graph, if it comes to a complete stop at 0,
If it comes to, no, say this. If it comes to 0, it comes to a complete.
yeah, once it hits 0, it comes to a complete stop. And
Yes.
then if it comes to a stop, it gotta change directions.
It could. because they actually could just stop and just go back in the same direction. But if you see it in positive, 0, then negative, or negative, 0, positive, it changed direction.
But in this case, for number 5, it's just saying, it's not like the other graphs where if it's on 0, it's at the same position it started because the starting position was 0. But for this one, it's not 0 because it keeps going.
Because if that was the other graph, it'd be a position time graph. That 0 means the starting position on position time graph. But because this is a velocity time graph, 0 means I stopped,
Comes to a complete stop.
complete stop.
And whether or not you change directions is dependent in a velocity graph.
Yes.
Okay.
There we go. And then that comes back to the very last one. Now, I remember Cassie said it. For 2, right? The rocket is traveling with a greater speed during the time interval from 0 to 1 than the time interval from 1 to 4. Now, say the exact explanation of what you said.
Sorry, which one?
2.
Oh, about number 2. The steeper slope shows that it's gone at a faster rate of acceleration, but the speed itself keeps up.
Exactly. The interval from 0 to 1 and 1 to 4 represents the acceleration, like that slope, like that interval. But we're not talking about acceleration. We would just know which one has the higher speed. So you actually could just look at the individual point. That's, remember when we talked about that instantaneous velocity, instantaneous speed, that's where this comes in at. So in this one right now, we don't have to look at the slope, the whole interval from 0 to 1. We just look at that one at that one point to see which one is higher. Because if we were looking at the slope of the velocity time graph, we're really talking about acceleration. That's not what we're talking about right here. So really, this is very complicated, but it's a complicated way to get you to understand. You just got to figure out how to read the graphs and know what you're looking
So I
for.
just need to see more velocity graphs. I never, if I did work with them, I don't know, but this is the first time.
But this is just a little appetizer to the practice problem. So now you know when you go to the practice problems, it's like 4 or 5 of these type of questions. They really just repeat each other. Like the questions are like the same. So now when you've seen this one, and this one is like a very difficult one, now you should be able to go to other ones and play around with them. Plus you have the answers. So let me see. We got graph and summary. Yeah, so we got like 2 more, and then we go through equations, and then we go to problems. So we will definitely get through this tomorrow. Not tomorrow, sorry. What is that? Thursday. Wednesday. Jeez. So we'll definitely get through this on Wednesday, right? Yes, I will come off and I'm gonna stop recording. And actually, no, I'm not gonna stop recording. Let me go back real quick and make sure I get through. Class is basically over, but I'm gonna make sure I go through 2 again. Just because somebody might need this later on too. So going back to number 2, right? The rocket is traveling with a greater speed during the time interval from 0 to 1 seconds than the time interval from 1 to 4 seconds. So no, right? We're saying no because if we look at the interval from 0 to 1, we're looking at the rate of change of the velocity from 0 to 1, and then the rate of change of velocity from 1 to 4. The rate of change of the velocity is actually speaking about the acceleration. We don't want to confuse the acceleration with velocity. We're talking about the velocity and trying to figure out if it has a greater speed, right? But if we look at the interval, then we're talking about acceleration. So we don't want to mix the 2 together. So that's why for this one, all you have to do is really just look at the point. So like this one is 40, then this one is 100. So you could just say this one right here has a higher speed at that point, instead of looking at the whole entire interval and calculating the slope. Does that make sense?
Yeah, but I still need to like practice.
Okay, cool. Yes. So in the meantime, right, I'm going to change the due date for practice problems 1 until after. It's going to be a week from when we finish it, which is to be tomorrow. So if you already submitted it, you're fine. But definitely go play around with these. This recording should be available in like 24 hours. So as soon as it's available, I'll upload it to YouTube. The other one I put on YouTube too, so I'll send a link to that as well, so that you can go back and watch this. Hopefully it's clear enough so we can hear everything. But play around with these. We're going to do this on Wednesday. Any questions online? If not,
No.
free to go.
Thank you.
No problem.
Thank
And I'll
you.
be stopping recording now.